and quality from farm to fork, which we're really pleased is being led by Hamamatsu. So first, I'd just like to give a brief introduction to Agri-Epicenter, which I shall just share my screen. Here we go. So can you see my screen? Yep. Okay. So there we go. So I'm Rebecca Lewis. I'm a new business and proposals manager at Agri-Epicenter, which means I get involved in our collaborative R&D pipeline and helping our members to develop projects and consortia mainly for grant funding. At Agri-Epicenter, we aspire to be the go-to enabler for innovation in precision agri-tech. And we work really right across the whole spectrum, from engaging with governments and academics and researchers, technologists and engineers, right through the food supply chain to technology startups and SMEs, farmers and the food industry, as well as the investment community. Our membership network currently stands at 192 as of today, which is something we're really proud of, and we support our members through helping them to secure funding for R&D, through providing project management services, links across the industry, including internationally, as well as providing technical expertise, R&D capability and facilities, our farming network to provide commercial test beds for agri-tech, and in many other ways as well. We have UK-wide coverage, which is illustrated on the map there, and I'll come on to that a little bit more in a moment. Our strategy is to try to build an ecosystem for innovation and collaboration in agri-tech. And we do this in order to help to support the food system to become more productive and towards carbon neutral, efficient and circular, and profitable and resilient. So the way in which we do this is through our membership, which I just mentioned. So building a community of innovators. We provide hubs to incubate startups and growing SMEs. And we also provide a number of events for networking and in engaging the industry with sort of relevant topics around agri-tech. In terms of our R&D capabilities, at the lower TRL end, we provide a lot of facilities and technologies to support development of technology. For example, remote sensing for crop disease detection, growth patterns and stress indicators, as well as on the animal health side, technologies to support animal health, behavior, welfare and productivity right across the species spectrum, and also including aquaculture as well as farmed livestock. At the higher TRL end, we support through testing, validation and demonstration across our farm innovation platform, which is our network of 25 satellite farms located around the UK and representing all of the main farming sectors. It also provides a really good base for knowledge exchange and engaging technology developers with farmers and end users. And then on the primary product quality, we have a food lab, which is one of our newer developments, which includes capability for VOC analysis, sensory evaluation, texture analysis, and also hyperspectral imaging. Our membership network, as I've already alluded to, is something we're really, really proud of. And it consists of, as I said, actually 192 organisations as of today, which spans right across startups and SMEs to global technology companies, household brands and leading research institutes. Just very briefly, our sites, as I mentioned, are indicated on the map there. The red dots are our main hubs. So up in the north, we have our northern innovation hub just outside Edinburgh, and down just slightly south at Dumfries, together with our partner SRUC. We have our CARF Innovation Centre. Then in the Midlands, where I'm based now, we have our Midlands Agri-Tech Innovation Hub, which has incubation facilities for businesses, as well as in association with our partner Harper Adams University, our Midlands Dairy Centre in Piggery. At Cranfield University, moving south, we have our crop tech, houses most of our crop technologies, and also new incubation facilities there in our Agri-Informatics Centre. And then in the far south, in Somerset, we have our Southwest Dairy Development Centre, which provides a really good test bed for all things dairy, really, and dairy technologies. So now I'm really delighted to welcome Hamamatsu and to introduce Kevin Mckechnie, who's going to talk to us today. So Kevin graduated from the University of Strathclyde in 2018 with a master's degree in physics, focusing on solid state physics and nanoscience. He's then moved to Hertfordshire and joined Hamamatsu as a sales engineer, and is a member of the analytical and medical group. And as part of his work at Hamamatsu, he's looking to get involved with agri-food companies in order to bring cutting edge technology to this market. So welcome, Kevin, and over to you.
Hi, thanks for the introduction. So that's, yeah, perfect introduction. So what I'll do is I'll just try and share my screen. Just give me a second. And then hopefully everyone will be able to see this presentation. Is that?
Yeah, that's perfect. We can see your screen, Kevin.
Excellent. So is it the presentation, or is it in the kind of presenter view? Because I'm not 100% sure what screen it's on at the moment.
Yeah, I think you just need to put it on presenter view. You can just see the mini slides down the left.
A second. It seems to jump into the other screen. Should have practiced this before. There we go. This is what it needs to be. There we go. Is that better? Perfect. Excellent. Okay, so yeah, so the theme of this presentation I'm giving is farm to fork. So essentially just showing how miniaturized photonic technology for food quality and safety can be used at many different stages of the agri-food journey, essentially. So coming up, I'm going to give a quick introduction to who Hamamatsu are, because I'm not sure how many, if any of you, know much about Hamamatsu. And then I'm going to discuss some of these miniaturized photonics technologies. A lot of the stuff will be perhaps telling you stuff you already know about why these are being used, but I think it's important to kind of contextualize why this technology is important. So here's Hamamatsu are a Japanese company based in the city of Hamamatsu. Founded in, as it says there, 1953. We now ship to over 100 different countries worldwide. Have over 15,000 different devices, units, systems, products, essentially. I think that's up to over about 16,000 now. We've got a very high sales turnover of $1.3 billion. So quite basically putting that money back into technology. So we have about 10% of our turnover is put back into R&D expenses, basically to always be pushing to develop the next technology and to see what the future will bring, instead of just reacting to what's happening. So we really want to be driving the way that technology is going in photonics. Over 5,000 employees in 17 different countries, 10 different research and production sites in the city of Hamamatsu, and a lot of information there about what our main business has been throughout our history, which is PMTs. So we started off as a PMT company, so we have 90% global market share of PMTs. But that's not all we do anymore. We're not just PMTs. We've got many different technologies across many different divisions. So, like I say, it's a global organization. So it's headquartered in Japan. That's where all production, R&D, and everything is. We have some sales offices in Japan as well, and then obviously we have some offices in Asia and Oceania, and then the Americas. Part of that is to do with the fact that Europe has a lot of different cultures, a lot of different, basically cultural differences between countries. So, you know, there's no point in someone in the UK trying to sell to someone in France. So we all have a local presence really to engage with companies in those countries and to really build relationships. So many divisions. We've got a solid state division. They develop basically our silicon and compound semiconductor technologies. You know, lots of different technologies within that. Then we have the electron tube division. So that again is PMTs, X-ray devices, things like that. That's what our kind of workhorse. That's what we started with. Systems division. So we manufacture all our own parts. Typically, the majority of our parts are components. But what we do is actually we also integrate these into fully blown systems ourselves. So every component within that will be a Hamamatsu component. Really just basically making sure that it's the best technology available within that. And then one of our newest divisions is a laser promotion division. So it's to do with our new laser technologies. So semiconductor lasers, high power lasers, things like that. And then, as I mentioned, we put a load of money back into our central research laboratory and to our industrial development centre. So this is really to have both fundamental research on light and new technologies, and also to create new industries. So that's a little bit about Hamamatsu. More than welcome to have any questions about that later on. But moving on to one of the things that I want to talk about, which is miniature technologies. So miniature technologies, one of the key things that these, so as we know, as I'm sure we all know, analysing the food quality and safety can come at many different stages. It can come, as I said in the title, farm to fork. It can be done when, you know, food is being grown, when it's being picked, sorted, packaged, even can be done in you know, stores essentially. So using these miniaturized photonic technologies allows it to be done more frequently at more stages of the process. If you only need a small handheld device, then it really opens up the areas where you can be big production lines essentially. Also, photonics is very high speed. It's very high speed sensing, and also you can get greater accuracy than with other technologies. Obviously, there's pros and cons of every technology, but with the photonics technologies, high accuracy, greater accuracy is one of the key features. So, like I say, the small size and low power of these mini devices means that you can get this high speed sensing and this good accuracy, even by integrating it into, like I say, harvesting equipment or things like that, which I know is not something brand new, but by miniaturizing more advanced technologies, it's something that we can that can really be continuing to develop. So as I say, even by using something simple as an RGB, so red, green, blue color sensor, it's possible to reject food that's the wrong color, such as tomatoes. So that's something that I'm sure we're all aware of that goes on. So that's something really simple. We do these RGB color sensors along with proximity sensors. So I'm sure we all know how they work, but essentially 3 filtered photosensitive areas to give an indication of the color of an object. So the system can be automated to reject objects showing too much blue and green, and therefore you only get nice red tomatoes. So that's something that, you know, like I say, it's not new. It's not something that should be surprising that happens. Oh, that image has come up a bit early. So, but essentially, as I said, these RGB color sensors can give quantitative information about an object, but it only gives it in 3 color bands. Using spectrometry or even hyperspectral imaging can allow more color bands essentially, so you get a more detailed build-up of the color of an object. Of course, these can be used not just for color. It can be, you know, you can look at absorption bands of certain compounds, and this can allow for measurements such as sugar content, bruising, and ripeness. Knowing about the chemical bonds and knowing about the chemicals within food can also help you to essentially, as this image here shows, build up an idea of the nutritional information of it, which is something, again, that's very important. So having advanced miniaturized technology that is able to give you this quantitative information is really, really helpful, and it's something that I think is going to become much more. So like it says here, being able to detect the quality of food early in the process can increase the yield and reduce wastage of food, which is something that in this day and age is something that's very important. And yeah, it can allow labeling and nutritional analysis to be much more accurate. So again, that's not anything that I think is going to be brand new for everyone. Here is one of the technologies that I want to discuss, which is the mini spectrometer. So as discussed before, that was just kind of giving some context to why spectrometers are useful. Spectrometers, as you may know, are typically quite large, expensive benchtop devices, and they're not all suited to use in handheld or mobile areas, or field measurements, essentially, not necessarily an actual field, but more non-laboratory based measurements. But Hamamatsu at our Central Research Laboratory have developed a range of small scale spectrometers that remove the need for measurements to be made in the laboratory. So that's one of the things that we think is really important. Here's basically a little image of our lineup. So we have the going down to fingertip size there. So these mini spectrometers employ special grating and special optical design inside them to basically enable us to reduce the size while maintaining high accuracy and high resolution. So essentially, this is what the larger units here are like. Then we have an image sensor, and at the other end, an input slit. And between that, we have a series of lenses, gratings, and focusing areas to essentially channel this light onto this sensor to give you an image of the full spectrum at once. So they can be done for really high speed measurements. Again, incorporating USB interfacing, so USB power, USB connectivity with a computer, it really means that you don't need power supplies, you don't need anything, you just need a laptop in this device and you're able to make spectral measurements. So that's something that, again, can allow remote sensing and real-time analysis. So that's something that we think is, really going to be quite useful. That's why we're trying to develop these technologies even further. So that was the mini spectrometer. We've pushed it even further and developed the micro spectrometer. So this is using micro electromechanical systems. We have managed to develop these down to fingertip size. So these are full working spectrometers that give you a full spectrum, but that are ultra compact. So these are the devices that we think are perfect for integration into other systems, and they basically combine high performance with low power and really small size. So this is something that you can have many of in a farm or in a kind of agricultural setting, and it's something that's it's low cost as well. So that's something that really we think can help push the analysis and the analysis of these crops and plants and everything, and food especially, into lower cost, more regular done, so can really improve the quality. So here's a little image of some of them. So like that's a 1 yen coin, but the size of a 5 pence. So get an idea of the scale of these devices there. We've been able to reduce the size of these by using a unique structure where many of the components that we saw in the previous image are actually combined into one part. So what we have here is the reflective concave glazed grating, which is a bit of a mouthful, actually is combining the focusing lens, the mirror, and the grating all into one. So what happens there is it really reduces the path length, reduces the number of components, and really can reduce the size. That managed to get us down to fingertip size. To push it even smaller, to the smallest one we just saw, what we've essentially done is just shorten the distance, but add in a secondary reflecting mirror. And what that does is that allows us to basically further reduce the size. And by using these high accuracy gratings, we can still get really good results, good sensitivity, and good resolution in these devices, despite them being fingertip size. So that's something that is really going to help these become more used in handheld devices, which will mean that food analysis can be done at the point of where the food is, and it doesn't have to be taken away for analysis. It doesn't have to be done in any sort of lab. It can be done in the field, quite literally. So that was more about food quality, so sugar content, bruising, ripeness, etc. But obviously, while we know that's important, food safety is even more important. So by using photonics such as these mini or microspectrometers, as I said before, information regarding the chemical composition of the food can be gathered and analysed. This can help, like I say, sugar content or bruising, but it's also possible to detect allergens or even toxins left over from this food sorting process or the growing process. So by detecting these unwanted chemicals, it can prevent cross-contamination during sorting and packaging, and again can help reduce food waste. So that's something else can increase the yield. It's really something that if we can get these technologies at every stage, we can be analysing at every stage of the process. So using small-scale photonic technologies, it's possible to have these scanners in shops or homes. So these are low-cost, small size, low power. It's even possible to have these in, in Tesco next to the fruit and veg, where you can look and you can say, let's say that apple doesn't look quite right. You can scan it with these scanners and it will give you the quality of the food. So again, it'll increase consumer confidence, and also will help basically, again, reduce food waste. And again, that's something that is really important at the moment. So make it easier to remove spoiled or rotten food from shelves, reduce incidences of food poisoning, reducing food waste by allowing people to check the safety of food before throwing it out. Like I say, you can have this in your home, and it would almost remove the need to just go by sell-by dates or the sniff test. You'd be able to just test something with these devices. So these technologies, miniaturized technologies, can also be used to remove unwanted foreign objects from food, such as plastics. So this is more getting into hyperspectral imaging rather than just spectroscopic imaging. But this is something that, again, by creating these small size, compact devices, we can create other devices and other systems that can be integrated into. Which again, if every component is really small, then you don't need to have a large system, and you'll be able to remove unwanted foreign objects within foods, such as, like I say here, plastics. You can see in this image, I think the images, the green circles are plastics and the red circles are actually little stones. So it's possible using these hyperspectral imaging to detect these different things. So that's just a little bit of a taste of the technologies that we have, and essentially why we think that these why we're looking to get involved with the agri-food market, because we can see that there's it's not that these technologies don't exist in the agri-food market at present. It's just that we feel that there can be more of them at more stages, and miniaturizing, I think, will help to do that. So essentially, why Hamamatsu? So as I said, world leader in photonics, a one-stop shop. We have everything from components up to cameras and full systems, quality and reliability, high quality products, and application variety. So like I say, it's not necessarily just at any stage of the agri-food process. For all stages, all different things, and we even have for LiDAR, for remote sensing and things like that. We have a lot of different technologies. I've just focused on one really small point there. Cutting edge research, so we're always looking to develop new products. Customization with in collaboration with other companies is always something that we're open to. And again, we don't necessarily just want to be a supplier. It's not that we want to help develop these projects, develop these products, and help other companies reach the point where they can achieve their goals. We're not just looking to make a quick buck. So thank you for listening. Like I say, any questions are more than welcome, and hopefully it wasn't something that you've all heard before, or if it was, hopefully at least it was interesting.
Thank you, Kevin. That was really, really interesting, and yeah, quite amazing to see the sensor the same size as the little 1 yen coin. Yeah, that was great. Thank you.
No problem. I'll stop sharing just now.
Okay.
There we go.
So at this point in these sessions now, we usually sort of hand over to our audience to do some introductions, and I think Florian from Muddy Machines is going to give us a bit of an introduction to himself and his business. So Florian, over to you.
Yes, thank you, Rebecca. Thanks, Kevin, for having us here. The way I'm going to share my slides is they're going to appear behind me. So if you just pin me as a speaker, then you should be able to see what I'm showing you. I won't take an awful lot of your time. I'm just going to share with you a little bit what we're up to at Muddy Machines. So my co-founder Chris and I, we started this company about a year ago. Agri-EPI has been helping and supporting us massively along the way. So big shout out to them. Always very, very good introductions that come our way by Agri-EPI. So we are essentially tackling two major problems in the world and in farming today. So number one, I think the one that affects all of us, if we want to have a peaceful world going forward, we have to solve the food supply question. How do we feed 9 billion people by 2050? That's going to require 70% more food production. And as you know, we only have one Mother Earth, right? We can't just find another planet as of yet and grow our food there. So we're gonna have to find some really smart ways on how to grow more with the resources that we're given. And because we also are not going to achieve that by using more and more pollutants and fertilizer, the way forward is probably, in our view, some really smart things around data science. But if we don't want to, in the short run, see the empty supermarket shelves again that we've seen in COVID, you know, we have to first fix the existential labor shortage problems that farmers have. You've seen it in the news last year. We had about a 30% shortage of field workers. Crops were rotting in the fields. This year, we've heard that farmers are beginning to reduce their output. And this is not only a problem in the UK, other countries have the same problem. And again, because of carbon emission targets, we can't just food import our way out of this, right? Every ton of fresh vegetables that we import, as opposed to growing them here in the UK, is going to come with several times the amount of CO2 emissions that we should really save. So what are we doing at Mckechnie Machines about this? Well, first of all, we're building robotic harvesters. Our first target crop is the immensely labor-intensive green asparagus. So we're building a robotic harvesting business. Yeah, we are removing this labor bottleneck so that farmers have a cheaper, actually more effective and more reliable access to labor. And farmers are literally banging on our doors and asking, when can we get the first robots? It's a very, very severe problem. So we're really enjoying very good engagement from the grower community. But as a side product of robotic harvesting, we're generating an unprecedented data set of crop performance growth as we go along. I'll spare you the metaphor around cookie tracking and advertising, but you can, I think everybody here is data minded and innovation minded enough to understand what it means if you can suddenly understand day 1, day 2, day 3 of harvest, how is the crop growing? How is that different from one part in the field to another part in the field? And what kind of learnings can we take from that? How can we adopt the inputs that we're using? How can we adopt our expectations on yields? This is going to be immensely powerful for farmers to have. So let me talk to you a little bit more about our progress on the asparagus harvesting front. We have built this little machine and tested it in the field this year with the largest UK asparagus grower. We call this the Sprout. It is essentially a four-wheel drivetrain that has a harvest implement in here in the middle. So this is a end effector that goes down and picks the asparagus as it drives over the field that way. Kevin, you might wonder what kind of camera technology are we using? We're currently using a high-res RGB camera with 2 depth sensors and an infrared projector. And this is just for spotting the asparagus. This does not yet include how the machine itself navigates on the ridge and into the field. Let me show you a quick video. Let's see if that works. Yeah, so this is the machine in the field. Up there you see today's asparagus rig as it is used by the advanced growers. You have about 10-15 people working on one rig. This tractor just is basically a box carrier. Yeah? So they walk behind the tractor. You need a guy to ride the tractor. You need a person to supervise this team. And in the meantime, our machine is happily ticking away. This is the Chin family. They produce about half of the UK's asparagus and have a massive packing operation where they pack about 80% of the UK's asparagus. So they know what they're doing, and they were impressed enough to put in a pre-order for next year to have us harvest several tons worth of asparagus in these fields near Ross-on-Wye. Yeah, so that's pretty much all I wanted to talk about. We are currently raising a seed round, so we're looking for up to £2 million of capital. I know this is not an investor audience, but I'll be remiss to not mention this. Very good. Any questions? Please shoot. I think I've stayed well within my 10-minute limit. Back to you, Rebecca.
Thank you, Florian. That was great. I don't think we have any more slides from any of the audience, unless someone would like to briefly introduce or present themselves. But otherwise, if you have any questions for either for Kevin or for Florian or for anybody else, then please use the chat function, and we can take those questions. Also, if you'd just like to introduce yourself, then please use the chat function just to say who you are and who you represent today. But on to questions. So first of all, we have a question from Duncan, who's from Agri-Epicenter for Kevin. And Duncan asks, are the microsensors static, or can they be moved over a growing crop? For example, in a controlled environment growth chamber?
Yeah, so the devices themselves are, they're not scanning or anything. They just analyze the area right in front of them. But part of the making them such a small size, making them so small, lightweight, and all this sort of stuff, is part of the idea is that they can be put on, they can put on a movable rig, or they can even be, a lot of them are able to be fiber coupled. So you can have the actual sensor at a certain point, and then you can have an optical fiber able to scan across anything. So I'd say it's a bit of both. The sensors themselves are static, but they can be moved around without affecting them. The only thing is excessive vibration would be the only issue, which again is why fiber coupling is something that we do a lot of. So optical fibers, so you can have that as essentially a sensor head connected to the device. So and again, this is something that the small size and the compactness is designed to allow you to essentially do whatever you want with them.
Okay, thanks, Kevin. A quick one for Florian now, from Christian. Are muddy machines associated anyway with muddy boots? I think that's a quick one for you to answer, Florian. Florian, do you want to come off mute? No. Okay, we'll perhaps come back to that if yeah, Florian's able to reconnect again. I had a couple of discussion points, I guess. So if anyone would like to join in, feel free to come off mute and just chip into the discussion. So Kevin's introduced a wide range of different applications for photonics technologies. I wondered where people thought the most promising use cases or the most promising applications might be. I wonder if Derek from JHI has got a view on that. Derek, I'm going to pick on you. I hope that's okay.
Sorry, can you repeat that? I sort of broke up there a wee bit, Rebecca.
So, sorry, I was saying we've been introduced to a lot of different applications and use cases for photonics technologies. I wondered if you had a view on what were some of the most promising applications within the agri-tech and food chain.
Taking the human out of any of the supply chain is obviously useful. So process control is going to be really useful here. I think potentially integrating them as well with Mckechnie pickers is an obvious one, because certainly working with a lot of the soft fruit industry, the guys there that are looking to pick strawberries, the obvious candidate at the moment. So using the technology to pre-program picking, so it's not absolutely right, but right when it eventually gets to store. So building in algorithms and data for that type of thing would be good. Again, I think Kevin mentioned already, having them in store. And I would imagine most of the retailers and their buyers would be interested in that aspect. Well, actually, they'd be interested, but push it down to the growers. They probably would want it themselves, if we're brutally honest. I can see the applications as well for mainstream crops. So looking at things, if the analysis can be more sophisticated or the range of wavelengths spread, looking at putting them onto things like combine harvesters would be useful for really early predictive quality for what's coming out on cereals, whether it's protein, whether it's disease, because mycotoxins are a big problem in that range. So as a scientist, I can see 1,000,001 applications for this. But given the fact you've gone down the miniaturization route, I think you're a country mile ahead of many of the competition there for applications. So I'd be interested. Interestingly, I was speaking to others in Agri-EPI about the combine harvester piece already. So Gavin Dick is the guy I'm chatting to about that. So maybe bringing this in would be a useful one to chat about there. Okay.
Thanks. Yeah, thank you, Derek. That was a great answer. Thank you. And yeah. So I suppose again, sort of Derek's touched a little bit there, but what would be some of the barriers to the uptake of these technologies? Anyone, please feel free to chip in, come off mute and turn your video on and answer. But in the meantime, David Armstrong, since you've just introduced yourself in the chat, I'm gonna pick on you if that's all right.
I'll unmute myself then. Yeah, I suppose the obvious challenge would be, and sorry, hello to fellow Strathclyder Kevin. I'm down the hill from the physics department in the tech building. Anyway, it's probably robustness, I would imagine. I mean, we involved in sort of practical applications of photonics, and one of the things we have to be mindful of is when we're designing things and systems for literally field applications. So its robustness is not entirely dissimilar from maybe military applications, when you know things will be dropped, kicked, and get dirty. So that's probably a significant challenge. We've perhaps early on in our activities in Agri made it easier for ourselves and done some activities in growth chambers, which are a more benign environment in that the devices and the systems are sort of static, essentially. But thinking to what Derek was saying about applications in bolting something to the underside of a combine harvester or a robot as it's trundling around, its robustness. So it's going back to what Kevin was talking about. It's designs of photonic systems that are not so sort of sensitive that they can't deal with a bit of punishment. So solid state designs, and that technology is there. I mean, as Kevin demonstrated. So it's not tomorrow's world. These things are kicking about. Even Kevin's talk was a lot about the spectrometer sides. We do work on the laser side, so quite often you need to shine light at something, so to generate that light. But there's classes of lasers, semiconductor lasers, that are robust and are designed for industrial applications, so they'd be suitable. So sorry, that was a bit of a long-winded answer. It's robustness. It's making them small, boltable onto a robot or a combine harvester. But I think that's doable. One of my colleagues who sits to my right, his background is in sort of military photonics. So you're designing something that will go in a tank, and I'm perhaps pushing it a little bit too much, but that's not entirely dissimilar to a combine harvester.
Yeah. And I guess when we're talking about the transmission and detection of essentially of light, then I guess contamination from things like dust and soil particles, or just the changing light conditions that you have in a field, I wonder how difficult or easy is that to overcome? And
yeah, totally. Sorry, I was going to say there's one. So there are increasingly now, in terms of sort of less than benign environments, where you've got dust and scattering and so on and so forth. There's classes of detectors, and Kevin will know more than I do about this, that can literally detect single photons. Okay. So you're down to very sensitive light levels, so you don't need pristine conditions. So these kind of detectors are used for imaging through dust clouds and sandstorms and so on and so forth. So the technology is there to deal with fairly scattering, turbid environments, including underwater, for example. So again, you can deal with pretty poor light levels in your turn signal. So that's doable.
Thank you, David. That's great. Another question's come in from Duncan. Does micro size mean micro prices too? And I guess we see this, a lot in agri-tech. There's fantastic technologies and solutions, but one of I think the biggest challenges is not even necessarily technical, but commercial. So how can we, I suppose, how can we ensure that these technologies are viable commercially and can can reach the market, and we can actually see them out on farm or within the food supply chain. So I don't know who to put that to. Kevin, I guess, do you want to take that one?
Not yet. So I wouldn't say micro prices, but definitely lower price than a lot of other spectroscopic devices. That's another thing that part of the drive for making these microspectrometers has been to, by reducing moving parts, eliminating moving parts, by reducing the number of components and by reducing the number of materials that are used, it's something that it will reduce the price. And again, these are designed for mass production. So again, volume, higher volume reduces the price even further. But typically spectrometers are in the thousands of pounds mark. But these microspectrometers are only in the hundreds of pounds. So while it's still, it's not £5 for a spectrometer, it still does reduce the price, by a factor of 10 or so, which allows this, because that's really, the aim is not that someone buys one of these and has to use it for all their things. The aim is that if someone needs 100 sensors, that they can comfortably buy 100 of these spectrometers. So it's really, so perhaps not micro prices, but the part of the drive for this miniaturization, especially in the spectrometers, is to reduce the price as well.
Thanks, Kevin. Right. So Derek has a question. What are the range of criteria detected to date? So sugars has been mentioned, and ripeness. These are specific and multi-component criteria. Has anything else been done to date?
So I've got a bit of an answer for that. So yeah, so we have some kind of measurement examples of, I think one of them is fat content in bacon, and the other is sugar content in an apple and things like that. For these examples, we've designed a kind of demo module that's a small module with a built-in light source and everything, and it essentially does have to be in contact with with what you're wanting to detect, or at least extremely close. And again, this is essentially, it's half the story is what we're doing. So we have the capability to provide the detectors that will get you the information. That information then has to be analyzed to detect the the sugar content, to detect what it is you want. It's not, you don't just pop the spectrometer in front of it and it'll say, oh, this is how much sugar's in it. So obviously there's a bit of work to be done there, but yeah, other things that have been done is fat content in milk, and a lot of things, kind of oil content in water, and different chemical compositions in water is a lot of things that have been done to date. We have some, basically the smallest of the spectrometers we have is actually an infrared spectrometer, and then the second smallest is a visible one. So we have a different range of different products, basically aimed at different areas of the spectrum to allow different measurements to take place. So it's really, we're trying to open up as much possibility. It's not, we're not just saying, right, we have a spectrometer that does sugar content and you can't do anything else with it. It's really wanting to open up this area with as much technology as we can, essentially.
Okay, thanks, Kevin. So Derek also asks, how close do you have to be to the analyte? And then is delivering better resolution? Is this delivering better resolution than equivalent NIR systems and probes?
Yeah, so in terms of how close you have to be, that comes back to what David was saying about, you have to be providing light somehow. So it's possible to do reflectance measurements, and that will come down to how powerful a light source you have. If you have a really quite a weak light source, then you're going to need to be really quite close to the object, and again, so that you don't get as much noise. But if you have a really strong light source that's reflecting a lot of light, then you're getting a lot of information with that reflected light. So in terms of how close you have to be, like I say, that is very dependent on the specific setup, but it's possible to be quite far away, essentially. And then in terms of better resolution to equivalent NIR systems and probes, I'm not 100% sure what resolution those devices would have. But again, with the compact nature of the devices that we're developing, the resolution is not insane, it's not excellent, it's not fantastically high, because we've had to essentially by taking 7 or 8 components and putting them into one, there are trade-offs there, but we're still having a typical resolution of about 8 or 9 nanometers. So it's still quite a good resolution for a device of that size.
So Kevin, what I was thinking about was, maybe resolution was the wrong word, it's detection limits. So if you're going sugars, what are you going down to? Because that's the key point actually for most people. They've got windows on what you want to define. If it goes above it, often that's good, that's fine. But if it goes below it, that means often factories might, if it's something coming in, they'll go, no, not accepting that. So it's hitting tight analyte specific windows. I think that was the key point. So I wasn't quite sure whether that's in there. Because certainly, so a good example is if barley's coming in to be malted, it has to hit criteria. If you've got a probe or something, you would just put into it at several points and it would give you, I don't know, X level of protein, or presumably you can create several criteria from the one set of wavelengths. But you need to be able to measure to, I don't know, between X% and Y%. So that's the kind of thing I'd be looking for a photonic system to deliver on. Now, so for some things that could be micrograms, for other things it could be gross percentages, so quite high levels. Of course, that all depends on the calibration you're setting up. Yeah,
that's something that I don't think's been considered too much. But that's an excellent point. I think that's something that it definitely needs to be looked into, and I can. That's something that I'll definitely be chasing up with the research and development side, and basically asking a little bit more about, the suitability of these devices for that. But that's an excellent question.
Thanks. Christian from Rayscapes has got a couple of questions. Christian, I don't know, do you want to come off mute and ask your questions, just so that they so that I get them so that they come in the right context, I guess. Around, yeah. I know you're asking about the infrared or near infrared, and then your second question as well. Okay. So I'll hand over to you.
Thank you very much, Rebecca. Hello, my name is Christian Murray. Briefly, I've been into image signal analysis for 40 years. And so here I sit today. I've been through a range of IP. So basically my question today is to distinguish the difference between IFR and NIFR. And is that a consideration that you're using within your sensor hyperspectral titling? And are there any UV considerations that you're going to add on top of this?
Yeah, so that for me, yeah. So essentially, infrared and near infrared, in terms of our sensors, is essentially near infrared is up to about, well, it depends, about 1.9, 1.8, 1.9 microns. And beyond that, that's more mid-infrared for our devices. In terms of our microspectrometers, the smallest ones only go up to about 1.1 microns, but we do have other spectrometers still in our mini spectrometer range that go up to about 2.5 microns, so a little bit more into the mid-IR. In terms of hyperspectral imaging, we do have visible hyperspectral image sensors, and we have infrared image sensors. I'm not 100% sure the peak, like the maximum cutoff wavelength for the infrared image sensors, but it is something that we're looking at across the range. And visible into some UV areas as well with the visible one. So the full wavelength range is covered by one or more of our sensors. We've got solutions for pretty much everything essentially.
Right. And then my second question is, are you considering Q physics and biofield sensors at this time?
At the moment, it's not something I'm aware of. It could be something that there could be work being done on that in our central research laboratory, but that's not something that I'm aware of at this point.
Cool. Anybody interested in the future of biopolymer sensors? I'm up for talking on it. Thank you very much.
Thanks, Christian. Do we have any more questions or any more discussion points from anybody? Would anyone like to?
I was actually going to ask Christian a question based on his question, but it's two things. What's the origin of interest in UV light? It's just something that we're involved with. And what do you mean? Did you say Q physics? What was that, Christian? Sorry.
Quantum physics, sir. It's a very highly moving trend field coming out of certain of the high-tech institutes of the United States. We've been working with this technology ourselves. And so basically it's about biofield sensors. So right now we use individual sensors to map basically individual points. And so what we're doing is we're presenting a new technology that maps at nanoscale entire field areas continuously.
Interesting. The reason I ask, we're involved in quantum technology quite heavily, actually. It's our other part of our activity. So it's there's a big quantum program in UK, as you'll be aware. So we're involved in a big chunk of that. So that's interesting. Okay.
I was looking to reach out to you, sir. Thank you.
Okay.
And I did have one more question here. So, and the question was machine learning versus neural AI. And has anybody actually taken a positioning on the growth strategy of those two particular things? And is anybody aware of the legislative impact coming to AI? Thank you.
Questions. Kevin, David, Derek, do you want to?
I would argue I've not seen a single example of AI as I would think of AI. I've seen plenty of machine learning. But AI means you throw a spanner at the thing and it works out what it needs to do without referring to a human. Machine learning means I don't understand that, call a human. And every system I've seen is machine learning to date, not AI.
Just on that update, we are working on reportable AI now. So that should hopefully overcome some of those issues we've seen. But thank you.
Thanks, Christian. Does anyone else have any final questions?
Why not? If I'm sorry, go ahead.
No, go on, Christian.
Yeah, all right. So GIS. So who's using GIS as the foundation for their hybrid interfacing in the future? As a foundation framework of data representation, modeling, presentation. Anybody?
Does anyone want to answer?
No,
we use it a lot. Agriculture uses it all the time.
Yeah, but I'm talking now more formally to remove Excel spreadsheets, data streams, separate reports, and combining them into visual presentation data sets specifically. And I will not mention the brand we work with, even though they are the world's largest GIS provider and do provide the UK government, DEFRA, EA. And we're working closely with them on these solutions to start to free up the complicated data input for farmers. So it's all good that we supply all this wonderful data, but then how do we actually make that useful to the farmer on the ground at the end of the day?
Well, I'm seeing examples of GIS-based data with quality data getting put in for disease predictions and so on, put onto almost topographic mapping. So people can see, I mean, your eye and your brain's an exceptional computer, and it would much rather see a picture than an Excel sheet.
Okay, yeah. That's our mission. That's our mission over here. Thank you.
Thanks, Christian. Florian, did you have one more question?
No, not question, but just to reiterate to Kevin, I think with the hundreds of pounds per sensor, that's definitely going in the right direction. And it all comes down to the reliability of those sensors then at the end of the day. there's a severe beating that these machines take in the field throughout the harvest season, and it's fine to swap out parts, but you shouldn't have to swap them out too often. But we're really excited about the opportunities, because as opposed to combinable crops, right, with these selectively harvested field vegetables, you have time to take a good look at each bit that you pick and analyze that. And this can have some really significant insights that for the farmer, then where to store it in the warehouse, how long to store it for, how to play the wholesale market a bit better. So we should definitely have a chat offline.
Yeah, no,
on the
of
sensors.
course, that sounds fine.
Great.
And yeah, again, one of the things with these micro spectrometers is again, one of the drives is for robustness, and so that's something I think, you know, like I say, we should definitely have a discussion about that, because I think, you know, it could be something that could be of interest to you.
And we're more than happy to make any introductions if anyone wants to, you know, carry on the discussion or have more sort of, I suppose, private discussions with anybody on the call today. So do just get in touch with us, and we can facilitate those introductions for you. But otherwise, I will thank you all for joining us today, for all of your questions and discussion. You know, that's been really good, really informative, and we will you know, keep you all posted with our next events in the series.